Um, Last time we tackled some integration techniques such as the integration by parts, the algebraic substitution, trigonometric substitution. So this time we're going to tackle the last integration technique, which is the integration of rational fractions. Okay. So when our integrand contains rational fractions, such as in the form of some p of x and some q of x, wherein this p of x here and q of x are both polynomial functions. They are both polynomial functions. Okay. So using this technique, it is assumed that this px and qx is a proper rational fraction. It's a proper rational fraction. For example, the degree of this p of x is less than the degree of q of x. So the degree of px is less than the degree of q of x. Okay. If not, then we need to carry out the division first. Okay. So for example, we have 2 all over x minus 1 minus 3 x plus 4, right? And then if we're gonna combine this, we have x minus 1 then x plus 4, and then we have 2 multiplied by this one, we have x plus 4, and then minus 3 multiplied by x minus 1, right? So this is equal to 2x plus 8 minus 3x plus 3 all over the x minus 1 x plus 4, or it is equal to negative x plus 11 all over x squared plus 4x minus x. We have 3x minus negative 1 times 4 is negative 4. Yan. So this term here minus is also equal to this part, right? Okay. So these proper rational fractions have to be resolved or broken up. So their corresponding partial fractions before integration, this one, can be performed. Say the partial fractions or the partial fractions or simple fractions that when combined to form a rational fraction. Okay, so if we were gonna integrate this, say this is our given integrand, if we were gonna integrate this negative x plus 11 all over x squared plus 3x minus 4, we can use the partial fractions in terms of this, or we can rewrite this in terms of this one, right? We have 2x minus 1 minus 3 all over x plus 4 dx, right? Then from here we use its equivalent fractions, and then you can now easily integrate both terms. So we have the integral of 2 dx all over x minus 1 then minus 3 integral of dx all over x plus 4. Okay, wherein we have the integral of this one is that we have 2 ln of x minus 1 minus 3 ln of x plus 4, then plus c, right? So you can't still do it mentally. You can integrate it one by one. Say the integral of 2 dx all over x minus 1. So by letting u is equal to x minus 1, then our du is just dx, right? And then from here we can rewrite this as 2 integral of our du is equal to dx. So we have du all over our x plus minus 1 is just u. So du over u is 2 ln of u, wherein our u is x minus 1. So this is our answer. The same method will be can be used here. Okay, and what else? You can also combine this part, or you can do some simplifications here. If we have they call this function like this, you can rewrite this as the ln x minus 1. This is will go here, minus ln of x plus 4, and this 3 here will go to here, then plus 3. And then the rule of ln, we have ln minus ln, we need to divide this. So we have ln x minus 1 squared all over x plus 4 cubed and plus c. So this is now our final answer using the technique. Okay, but as you can see here, the denominators of the partial fractions, so this denominator here, are the factors of q. So the denominators are the factors of q of x, and there are 4 cases. So there are 4 cases rational fractions. Rational fractions. So we have 4 cases involved in the rational fractions, depending on the denominator. So we have case 1 is that the denominator consisting of one distinct linear factors. And for case 2, we have a denominator consisting of repeated linear factors. For case 3, we have denominator consisting of a quadratic factors. So for case 4, we have denominator consisting of repeated quadratic factors. Okay, so on the next videos, we will tackle each case 1, case 2, and case 3, or the denominator of the fractions which contains of distinct linear factors. We have repeated linear factors, quadratic factors, and repeated quadratic factors. So thank you, and see you on our next video.